Welcome to the Early Career Professionals in Mapping webinar series. The American Geosciences Institute has partnered with the National Cooperative Geologic Mapping Program to highlight the work of early career geoscience professionals, especially as it relates to the use and production of geologic maps. Each webinar will begin with a presentation from an early career professional, followed by an interview, and then a live Q&A session with the speaker. Today's presentation is by Shadya El-Ashkar, who will speak about her work Bedrock mapping with the West Virginia Geological and Economic Survey.
Hello everyone, my name is Shadya El-Ashkar and I'm a geologist at the West Virginia Geological and Economic Survey. This is my first career job in geology and I've been with the survey for a little bit over 3 years now. I specialize in bedrock mapping, so today I'm going to talk to you about mapping sedimentary rocks in West Virginia. But first, I'm going to tell you a little bit about myself and how I got to my current position. So here's a bit of background about me. I am originally from Salem, Massachusetts, which is where I attended college. I graduated from Salem State University with a bachelor's in geological sciences in the spring of 2017. During my undergraduate career, I had great opportunities, which included geology field camp, conducting undergraduate research, and being involved in various types of geological fieldwork and field trips. A highlight of my undergraduate experience was doing field camp in southwestern Montana, where we did bedrock mapping of the area around Block Mountain. In 2018, I moved to West Virginia to pursue my master's degree in geology at West Virginia University. My broad research interests were in sedimentary geology and paleontology. My master's thesis consisted of reconstructing depositional environments and paleoecologies from a series of Silurian-aged shallow marine limestones and mudstones. I graduated in 2020. I began working at the West Virginia Geological and Economic Survey in September of 2020, which is where I've been for the past 3 years and about 3 months. Over my time here, I've learned a lot about West Virginia's geology, and I've had many great opportunities to travel throughout the state for fieldwork and out of state for geology conferences. So before we really get into the bulk of what I do on a daily basis here, I'm going to provide you with some background information about bedrock mapping and sedimentary rocks. As a geologist, I make bedrock maps. But what exactly is bedrock? Bedrock is the solid rock that exists beneath the surface materials, such as soil, sand, mud, and other types of unconsolidated or loose sediment. Bedrock makes up the Earth's crust, which is its outer layer. When mapping bedrock, geologists look for outcrop. Outcrop is any bedrock that is exposed at Earth's surface. Sometimes the outcrop is concealed by loose sediments, rock debris, or vegetation, and we need to dig beneath these layers to find it. This is especially the case in West Virginia, where we have vast forests covering much of our land. Road cuts often give us some of the freshest, most extensive views of rock beds. So as you may know, there are 3 major rock groups. There's igneous rocks, metamorphic rocks, and sedimentary rocks. Now, bedrock maps can be made for all types of rocks, and they are. But however, in West Virginia, most of our bedrock is sedimentary. So a very small portion of our rocks are igneous and metamorphic, and you find those out in the Eastern Panhandle. That is out of my jurisdiction for mapping. I am in southern West Virginia, where everything is sedimentary. And so, sedimentary rocks actually account for over 95% of the exposed bedrock in West Virginia. So how do sedimentary rocks form? Basically, these are pre-existing rocks that are broken down into particles or grains through processes of weathering and erosion, and these particles get transported and then eventually become cemented or glued together to form a new rock. So we have all types of sedimentary rocks in West Virginia. We have conglomerate, sandstone, shale, mudstone, limestone, and one of our most prized possessions, I should say, in our state rock is coal. Coal is the state rock of West Virginia for a very good reason. We have a very rich history of coal mining in the state. Today, coal mining is still in operation. West Virginia's mineable coal can be divided into a northern coal field and a southern coal field. The coal fields in the southern part of the state are more mineable. Our coal deposits range from Devonian to Permian in age, where most of our commercially mineable coal is coming from Pennsylvanian-aged rocks, like the Pottsville group, which is one of the rock groups that I actually map, and we will talk about in a little bit later. The grade of coal found in West Virginia is typically bituminous, And coal forms in swampy environments over millions of years.
So as a bedrock mapper at the West Virginia Geological Survey, I am assigned to map the rocks in a designated map area known as a quadrangle. Each bedrock mapper is given one quadrangle per year. What does a bedrock map even show? So the bedrock map shows distribution of different rock types at or near the surface of a given area. And it also shows geological structures such as folds like major anticlines or synclines, and also faults. So there's a number of reasons why, just in general, bedrock mapping is important. Number one, we have infrastructure planning and building development, so you need to know the integrity of the ground that you're building on before you put a building there. Obviously, you don't want a sinkhole opening up, if you're building on something like limestone. We also have awareness of natural hazards, so we need to know areas that are prone to natural disaster, susceptible to certain earth processes. So like floodplain, obviously you don't want to build where your house could potentially be flooded. Same goes for like coastal areas, as well as landslide risk and hazard, stuff like that. Just understanding where you might be more prone for that to happen. We also have energy resource extraction. So natural resources such as oil and gas can be found in certain rock structures that capture and store the oil and gas, such as anticlines, which are a type of fold. And so bedrock maps can really help narrow down where to find these oil-producing rocks. The same can kind of apply for coal, whereas you want to know where the mineable coal is. So we map those coal seams as well. And ecologically, our bedrock maps are used, I know, by the Department of Natural Resources when they're conducting different species projects, different research about different species, vulnerable species in West Virginia. Um, a lot of times the habitats are closely linked to the geology. So think about bats, like the little brown myotis. They obviously like to live in caves. And where are caves? In limestone. And we also have understanding of how water is moving in the subsurface, which is essentially hydrogeology. This is very important for when contaminants enter our water streams, our water tables, and we want to understand how a potential contaminant or something like that is moving in the subsurface and whose water basin it might potentially contaminate. So as you can see, there's more reasons than this. But this in general is why bedrock mapping is very important. So here we are in our second section of the presentation. I'm going to be talking to you about field mapping and our different methods and what we're seeing out there. So field work is a major component of bedrock mapping. We need to observe as much outcrop as possible in our assigned mapping areas to really understand what's happening geologically. We make observations and collect data that make more sense later sometimes when we're actually creating the map and connecting those dots. Some of the areas we map are more developed residential areas that have just more people living there. Some areas are more rural with few small towns, unincorporated, maybe amongst acres of privately owned farmland or woods. And other map areas, which are the most ideal in my opinion, might be largely covered by national or state forests. In this case, usually no one's going to bother you. Not that we get bothered all that much, but believe it or not, the best time of year to actually map is in the wintertime. And this is because in West Virginia, we have a lot of green, and it's not called wild and wonderful for nothing. There is just a lot of trees and vegetation covering our gorgeous landscape, gorgeous geology that we do have. And so once those leaves come off, in the late fall, this opens up our view for the rocks tremendously. Although the winter weather can present its own challenges, like if we get enough snow that can really cover up our outcrops, that is not good. It's also very difficult to concentrate and think in, freezing temperatures, but we do make do with it.
Having the right field gear is very important to make observations about the rocks. These tools help us study and describe different properties of the rocks. So some of this field gear and all of this is essential. We have this digital tablet, that's how we take our notes and we view our maps. You can also have a paper notebook just in case you want to take paper notes. That is less common nowadays. Rock hammer allows us to break up pieces of the outcrop and look for a fresh surface of the rock. And scale bars are great for when you're taking photos and you want a reference to the scale there. So the Breton compass is a very important tool that we use in the field. This enables us to measure bedding planes and other geological structures and features. A hand lens is also an essential tool to have. This will magnify any view of a rock or feature that you're looking at. Grain size sorting and shape charts are not essential, but it's a nice thing, a useful thing to have in the field, especially when you're describing the texture of sedimentary rocks. And we have our hydrochloric acid, which this is used to test if a rock has calcium carbonate minerals. If a rock does have calcium carbonate minerals, such as limestone, then it will react in a way which means it fizzes. And last, food is very important to have, especially when you're going on long treks and you don't know when you're going to be coming out of the woods.
Over the past few years, the West Virginia Survey has adapted to all digital field mapping. The use of tablets have revolutionized how bedrock mapping is done. We no longer have to carry paper maps. We can load our base maps, such as our topographic maps, our LiDAR imagery, and previously mapped geology can be loaded into our Samsung tablets as digital files, which we can access anywhere even when not connected to the internet. The advancement of technology in field mapping has allowed it to become more efficient. Advantages of digital field mapping include automatically georeferencing data points, so your points will automatically be plotted where they were taken geographically. Another advantage is that digital data can be backed up, so this will prevent the loss of valuable data. And by far, one of the most major technological advancements we've had in field mapping is LiDAR imagery. So in recent years, LiDAR imagery has been released for the entire state of West Virginia. This has been a tremendous help for us when we're field mapping. LiDAR imagery shows the relief of the land, giving a three-dimensional view. Landforms such as cliffs and plateaus can be seen on LiDAR imagery. If you look to the lower left, this figure shows LiDAR with red lines delineating a massive sandstone. Oftentimes, rock outcrop can be seen on the LiDAR, and pronounced ridges can even be traced for long distances. This gives us mappers the advantage of visualizing where particular rock formations may be, in areas of the map that are difficult or even impossible to get to.
So what properties of rocks and rock outcrop do we note when we're in the field? First and most obvious is the color. This is the least diagnostic feature. Color can reflect the mineral content or composition of a rock, and it can be highly variable. Next is texture. This refers to the size, shape, and sorting of the grains within the rock. Sedimentary structures are an important observation to take note of. These are three-dimensional features that are typically outcrop scale. The example on this slide here is cross-bedding in a sandstone, which that is pretty common in the rocks that I map. And we also have fossils, which are indicative of certain environmental conditions and give us a glimpse of what some fossil communities look like. We also have bedding style and thickness. So is it thin bedded? Is it medium to massive? And how thick is the outcrop? You know, anywhere from 0 to 100 feet or whatever the value is. These are just important features that we like to note. Now I'm going to walk you through some interesting features that I've observed in the rocks I map. We're going to start with the oldest rock group that I have to map, which is the Greenbrier group. This group is Mississippian in age and is characterized by various types of marine limestones, many of which have a great abundance and diversity of marine fossils. The Greenbrier group is split into 6 mappable units. Colors can vary from gray of the pure limestones to a more tan yellow weathered color in limestones that are containing more mud. A typical feature in these muddier limestones are laminations, pictured to the top right. Pictured to the bottom right are stylites, which are also pretty common in the lower Greenbrier. The Greenbrier limestones are also known for excellent cave developments, and they are the top karst-forming rock in West Virginia. Rocks of the Greenbrier group represent deposition within a shallow marine environment. Next, we have the Mauch-Chunk group, which is Mississippian in age, just above the Greenbrier group. The Mauch-Chunk group is characterized by red shales and mudstones, various types of sandstones, and a few limestone beds, including the Avis limestone and the Reynolds limestone. I should also mention that coal has been observed in the Mauch-Chunk, or at least the upper Mauch-Chunk group. However, none of it is commercially mineable. The Mauch-Chunk group is split into 4 mappable units. Red is the primary color of this group. However, shales and sandstones can vary in color from maroon red, browns, tans, yellows, to olive greens. Sandstones in the Mauch-Chunk are typically cross-bedded. Some of the sandstones, like the Princeton, contain quartz pebble conglomerates at their bases. The youngest rock group I've had to map is the Pennsylvanian-aged Pottsville group. This group is characterized by massive white coarse-grained sandstones, which are typically cross-bedded. We also have quite a bit of plant fossils. There's a wide variety. Pictured here is Calamites, which could be like a plant stem. We also have Stigmaria, a fossil tree root cast, and fern fossils have also been observed. Now, the Pottsville group are coal-bearing rocks, and much of this coal is commercially mineable. This is a large source of our coal has come from the Pottsville group. Although not much coal is observed in my mapping areas nowadays, you can clearly see where coal was strip mined and quarried in various areas, and this is also very evident on the LiDAR imagery. Geologists group rocks into units called formations. Formations are packages of rock with distinct characteristics that are mappable on Earth's surface or at least traceable in the subsurface. Each color on the map represents a different formation. So here's an example of one of the rock groups that I map in West Virginia and how it's broken into distinct formations. There's also members that can be distinguished from the formations. However, formations are the fundamental unit that we will focus on. The Mauch-Chunk group is the group that I map the most in southern West Virginia, and it can be divided into 4 formations. In the next few slides, I'll provide a brief background of each of these Mauch-Chunk formations.
So starting from the youngest rocks to the oldest, we have the Bluestone Formation, which contains red shales and mudstones, occasional fine-grained sandstones, and it also includes the Princeton sandstone conglomerate at the base. So this is a prominent member that is essentially a marker bed for the bluestone. Below the bluestone, we have the Upper Hinton Formation, which largely consists of red shales and gray marine mudstones with occasional thin sandstones. This formation includes the Avis limestone at the base, which is a fossiliferous limestone. It can be micritic, it can be more crystalline. It is a quite variable limestone, and it often has a very high diversity and abundance of marine fossil fauna. And below the Upper Hinton Formation is the Lower Hinton Upper Bluefield Formation. This also consists of red shales and mudstones, which I don't know if you're picking up on the theme here, but the Mauch-Chunk group is essentially dominated by red shales and mudstones. There are different types of rocks as well, but for the most part, that is what characterizes the group. So all of these formations are going to have some variation of red shale or mudstone. So anyways, this Lower Hinton Upper Bluefield Formation also has the red shales, mudstones. It has red and brown fine-grained sandstones, and it also includes white quartz-rich sandstone members. We have 2 formally recognized members, the Stony Gap Sandstone and the Droop Sandstone, which are both gorgeous, usually medium-grained, pure white, quartz-rich sandstones. And last but not least, we have the oldest rock formation at the bottom here. This is the Lower Bluefield Formation, and it actually seems more distinct than the other formations just because it has more limestone, just more marine units in it. This is a marine influence unit, and it includes these prominent limestone, these formal members that we recognize. So we have the Reynolds limestone, which is actually at the top of the Lower Bluefield Formation. And then right below this, we have the Glen Ray limestone. And both of these limestones are quite similar. They have a lot of fossils, so there's a wide variety that you might find of normal marine fossil fauna. And just below the Glen Ray, there's what we call the Lilydale Shale Member, which is a quite thick package of shale it can be black, but it can also have all different types of colors, and it can have some thin beds of sandstone as well as thin beds of limestone. So fossils are not out of the question for the Lilydale either.
Now, I just want to jump back a little and take a little bit of extra time to show you some of the cool marine fossils that we observe in some of these limestones. So these images here are taken from fossils that were found in either the Greenbrier limestones or some of the Mauch-Chunk limestones like the Avis and the Reynolds. So we have Archimedes, which is a bryozoan. This is pretty common in the upper Greenbrier as well as the Mauch-Chunk limestones. Brachiopods, particularly the articulate brachiopods, are the most common fossil fauna that we find in any of these limestones. And they have a wide variety. Their shells have many different types of morphologies. Another type of bryozoa is pictured in the top right here from the Alderson limestone. And here's just a nice image. If you look in the bottom center, of this rock that is just chock full of brachiopods. A lot of times you might find a rock that is just essentially looks like a bunch of fossils cemented together. And then here to the bottom left is one of my favorites, orthoconautiloid, which is a cephalopod, so closely related to octopus. And just another view of some of the fossils we've observed. So to the top left here is some gastropod fossils we found in a lag in the Reynolds limestone. Here's another fossiliferous hash or lag that we've seen in the Glen Ray limestone just to the right there. There's some nice crinoid columns. There's another Archimedes fossil, and blastoid heads were found in the Union limestone, which blastoids are closely related to crinoids. And then in the lower right-hand corner, there's a rugose coral, which is a form of solitary coral. This was observed in the Alderson limestone.
Back in the office is where we analyze our collected data to make informed interpretations. Such interpretations might include identifying formations based on the descriptions that we've taken and reconstructing geological structures or features such as major folds like anticlines. So what are the final products that are included with a bedrock map? Each bedrock map includes a composite stratigraphic column, a cross-section, and a technical report. All these products, minus the technical report, are made using ArcGIS. This powerful program can take various types of data and compile it into informational graphics, which are formally published. The finished product looks something like this. All map graphics are displayed on one sheet known as a map layout. The bedrock map is positioned in the center of the layout, and this includes detailed rock descriptions, a legend, and a scale bar. There's also more essential information for reading the map, which is located towards the bottom. To the left of the map is the stratigraphic column, and this is an illustration of the vertical sequence of rocks arranged from the oldest at the bottom to the youngest at the top. The stratigraphic column shows the succession of rock formations in the same colors as they were mapped on the bedrock map. Stratigraphic columns really illustrate the different characteristics of each formation and are useful for noticing trends in the rock formations over an area. Different stratigraphic columns can be correlated if they contain the same unit or formation. At the bottom of the map layout is the cross-section. Geologic cross-sections are illustrations that show geological structures, such as faults and folds, in the subsurface. Geologic structures on the map are depicted in plain view, whereas the cross-section will provide a cross-cut view of the rocks, showing the relationship of these rocks based on the bedding plane and the structure measurements that we took at the surface with the Breton compass. These diagrams help us visualize how rock layers are behaving in the subsurface. A transect is drawn perpendicular to the major trends of geologic features. Now, I just want to briefly mention again the importance of bedrock mapping, specifically in West Virginia. So we have a lot of natural resources, coal, oil, and gas, and it's important to identify geologic structures that trap oil and gas, such as anticlines, knowing where these oil-bearing rocks exist in the state so we know where to drill for them. Coal bed mapping is also very important in locating commercially mineable coal seams. Um, More specific goals for our survey are finishing up certain areas of the state. So we've been working largely in the southern part of the state where we have completed a huge portion of the southeastern part of the state. And our goals are to really finish up mapping in areas that are pretty much almost complete. And we've also been prioritizing karst terrain, so limestones, like specifically the Greenbrier limestone, we've been tracing that group down from the north to the south to notice any spatial trends or changes that are occurring from north to south. So that concludes the presentation segment of my webinar, and I just want to thank you for being here. If you have any questions, you can save them for the live Q&A towards the end. Thank you.
Shadya, thank you so much for sharing some of the work that you do with the West Virginia Geological and Economic Survey. Lindsay and I are excited to dive into some of the details of your work and experiences. And we'll start off with a question that I have. You mentioned in your talk that you've had experience doing bedrock mapping in states other than West Virginia. How does the process of mapping differ between states in your experience?
So the process of bedrock mapping, the processes and methods are pretty similar. However, it can vary based on the type of rock that you're mapping. So as I mentioned, West Virginia is mostly sedimentary rock. So we're focusing on identifying certain properties of these sedimentary rocks, like different grain size or textural properties, as well as the fact that there are sedimentary structures and different depositional artifacts that you can find within sedimentary rocks. When you go to other regions that might have igneous rocks or metamorphic rocks, there's different features you'd look at. So for igneous rocks, you might look at some igneous intrusions and take measurements with the compass based off of igneous intrusions like within a host rock. Metamorphic rocks, you can look at the different phases of deformation. So like different folds, there might be a series of folds that have occurred, and you can reconstruct which ones happened first, essentially. There's also features such as foliations in metamorphic rocks that can often get measured as linear features. Some of the common features that you can have in any type of bedrock, whether it's igneous, sedimentary, or metamorphic, are faults and folds.
I have a question about just kind of where you got that information and where your other experiences were. Were they through college experiences, different field camps? You talk about where maybe you did some of that other type of mapping?
Sure. So actually, my first experience bedrock mapping was in Massachusetts, which is where I'm from. And we had structural geology, which is an undergraduate level course. And where I'm from, Salem, Massachusetts, it was all pretty much igneous rock. So we were mapping igneous bedrock. We were taking measurements based off of relationships between intrusive igneous bodies within host rocks, that kind of stuff. And my other experiences, so with that same undergraduate institution, we went to Montana, southwestern Montana, for field camp, which was also part of that undergraduate geology program. And there it was more sedimentary bedrock, but we did have some igneous intrusions in some of the maps that we did, so that made it kind of interesting to have different rock types on one map. Another place that I went to for bedrock mapping was Alaska. Again, that was all sedimentary. It was pretty different from, at least structurally, from what I'm used to mapping here in West Virginia, where my map area is very flat lying, or I should say, like, the rocks are pretty horizontal. They're not as deformed as they could be closer to where the major mountain building events were happening. But yeah, so when I went to Alaska, it was kind of a different world out there for me, because most of the sedimentary units we were looking at were either overturned or vertical. And there was like a lot of chevron folding, a lot of continuous anticline, syncline folds you could see just for even like a long stretch of the beach. It was just nice to have that continuous exposure there.
Nice. So why is it that there is so much sedimentary bedrock in West Virginia? What processes kind of like formed all of those rocks there?
Okay, that's a great question. So that really has to do with the plate tectonics and just where West Virginia was located geographically during these major mountain building events. So during the Paleozoic, and what was the North American continent, there was a series of large mountain building or orogenies occurring, and that is what ultimately created the Appalachian Mountains. So this was all happening on the eastern margin of West Virginia and just in general of that North American plate. Um, and so as a result, um, as these plates are converging and creating mountains, there's sediment that's eroding off of these highlands and it's getting deposited to the west of where the impact was happening. The concentration of that mountain building impact, we had a shallow interior seaway that covered much of West Virginia during the Devonian and Mississippian periods, different times during the Paleozoic, and then once the sediment kind of like filled those basins, we started to get more terrestrial deposits. So we had fluvial systems like river systems, deltas, stuff like that. Eventually, we get into more swampier wetland in the Pennsylvanian, and that's why we have so many coal deposits in our Pennsylvanian rocks because of that environment during the Pennsylvanian swampy and just like organic rich material is concentrating in these wetlands, and then over millions of years that forms coal.
And so you mentioned the coal, and within your talk, you talk about the Mauch Group and how it's not commercially mineable. Can you talk a little bit more about that specifically?
Yeah, so you can get coal seams in the Mauch, which is Mississippian in age, that it's middle to late Mississippian. However, a lot of these coal seams are either very thin. The coal grade is not bituminous, it's a lot lower. It wouldn't be efficient to use this as fuel, and it would cost more to extract some of this stuff from the earth, and considering that it's not the grade that we'd want to burn to actually produce energy, then it's not good.
Right. So one of the rocks that you talked about was limestone, specifically in the Greenbrier group, and that how they can form caves and karsts more easily than others. So can you talk more about like the formation of caves and caves that you come across in your work?
Yeah, so the main idea with cave formation essentially is that you have a soluble rock that's being dissolved. So your soluble rock could be limestone or dolostone. And when water percolates or trickles through fractures or cracks in the rock, it can expand and open those cracks into larger passageways and ultimately creating caves. Um, so I have had the opportunity to go into caves on the clock, which has been helpful for our research on the surface of just understanding how the different rock units are interacting, specifically around areas that we have, which are known as fault zones. Sometimes your fault is not exposed on the surface, so it can help to go underground and see if there's any fault expression in a cave. Um,
Nice.
yeah.
So are they still forming? Are these processes still going on where like new caves and other like sinkholes and things could form?
Yeah, I mean, I would say so. As long as there's weathering and erosion happening, as long as there's water, which is the main reactive agent there with helping the karst features form. Yes, I would say it takes obviously a very very long time, millions of years to form, but yes, they're still forming.
And are these features things you're gonna map? Like, do they make it onto the geologic map, or could someone look at a map and identify them from, what goes into that work?
So that's a great question. We do not, for our bedrock mapping at the West Virginia Survey, we do not map superficial features like sinkholes, and you can't always tell if there's a cave somewhere, just based on looking at just based on the aerial map view. However, there are some people that do map sinkholes, and you can see them very prominently in the LiDAR. There's some limestones that just are more prone to sinkhole development. There even is a map symbol for sinkholes, but we don't even map them. They're just so common in some of the areas that we map. We're really just focusing on the bedrock. But sometimes if you look at LiDAR imagery, the terrain can appear as almost Swiss cheese looking because you have all of these little holes. And that can sometimes be indicative of what a certain limestone member, essentially. So an example would be the Denmar formation of the Greenbrier limestone group. That formation tends to be characterized by sinkholes, and it's quite obvious when you look at it on the LiDAR.
Great. And speaking of LiDAR, in their talk, again, you mentioned the use of LiDAR in mapping. And you also mentioned some places that are difficult to access. And I wonder specifically about those difficult places. What types of technologies or techniques do you have to use to map those areas? Do you use LiDAR more often than you would in other areas? Are there other technologies you use?
LiDAR is definitely a huge advantage for field mapping. If you can identify a certain topographic feature or something like a cliff or a plateau on your LiDAR and actually go there and ground truth it, see what rock outcrop is there, and then take a step back, look back at your tablet, look back at your LiDAR, and see how far can I trace this ridge line. If it's making some type of topographic expression, sometimes like an example is the Princeton sandstone, which I talked about in my presentation. It's a massive quartz arenetic unit that forms these huge plateaus and also cliffs, and you can see it quite prevalently in the LiDAR, and you can trace it for miles. So that can be very helpful in areas that are either concealed or not concealed, but areas that don't have accessible road, areas that don't have road at all.
That's awesome. And so LiDAR, you mentioned, do you guys use drones or anything else to get that incorporate aerial views, or is that maybe to come later for West Virginia Geological Survey?
So I wish we did use more drones. We actually do not own drones at the West Virginia Geological Survey. However, I have a coworker who's also a bedrock mapper. He has a personal drone, which he's taken out a few times in his field areas. That has helped us map very tall cliff faces, like hundreds of feet that we just couldn't get to. We'd have to probably climb the other side of the backside of that mountain to get up there. And I personally haven't used drones. When I was a teaching assistant for a field camp at WVU, one of our instructors had a drone and he flew it around. You could get pretty close. Some of the drone technology, I think you could even estimate like strike and dip of a bedding plane, stuff like that. There's some disadvantages to having drones. I know that the instructor I was with at one point for that field camp ended up crashing the drone. It got too close to, yeah, I don't know if I should tell this story, but yeah, sometimes, your depth perception is off and you might hit into something and have your drone stranded, then you have to go hike up that big ridge to get it. But otherwise, there's definitely some great aerial views you can get, and especially for those tall cliffs that there's just no chance of ever climbing to.
Great. That sounds like a fun experiment to start using those technologies. Um, so when you're looking at rocks and you're out there mapping, you mentioned in your talk that you see different formations and I believe you mentioned laminations and cross bedding. So can you talk about a couple of the ones that you see most commonly, and what do they really tell you about the rock? Like maybe how it formed, or what indicators are you looking for when you're out looking at bedrock?
So probably the most common feature I see, at least in the sandstones, but even some of the limestones, is cross bedding. And there's different types of cross bedding. Some of the cross-bedding that I get, some of the cross-bedding I observe in the Ma chunk can be indicative of a unidirectional flow. So more of, think of a river system where there's just one current going. And these can these can produce features called ripples, which essentially cross beds or cross laminations are a cross-cut view of those ripple or dune structures. In the Pottsville group, there's a different type of cross-bedding that I observe. It's called herringbone cross-bedding, and that's more of a bidirectional type of cross-bedding where there's a current that's reversing. So there's two different flow directions, and usually these occur in tidal environments. So if you think of tidal inlet, where you have water moving in at a certain time of day, and then that current will reverse, and it will move in the opposite direction. Another interesting feature that I often get in the Mauchunk are concretions, and this is a common feature in any, not any sandstone, but concretions can be pretty common in sandstones. That's just a hard bulbous precipitation of minerals. Essentially, it forms like these nice concentric rings, and it's usually made up of the same, well, it is the same material as the surrounding rock. We can also get features called nodules, which kind of similar to concretions, but it's when a mineral different from the rock is essentially forming around a certain grain. I think laminations is also pretty common, which that's a pretty straightforward, that's a pretty basic sedimentary structure. Essentially, laminations typically occur in calm, quiet environments where um, finer sediment like silt and clay is allowed to settle out, and form these more or less horizontal or planar laminations.
And I'm guessing you're putting all this in your field notebook as you're looking at the rock and recording all that information. But does any of that information make it onto the actual maps?
So I would say on the actual Bedrock map, no, but so the stratigraphic column is where you can further characterize these rocks, and there's different symbology you can use to point out certain features. So if a certain rock unit has fossils, there might be a fossil symbol next to that. There's also, if you have like ripple bedded sandstone, there's a certain symbol for that. So the strat column definitely characterizes the strat column does a better job at showing the characters of the rock. I should also point out that there is a map unit description part that we do have included on the layout, usually placed to the right of the map, and that will go through and describe with more detail, basically the lithology, so like the rock type, and what you might expect to see feature wise, and also bedding wise, like is it thin bedded, massive bedded, what essentially geometry is occurring there.
Awesome. And Shadya, can you talk more about the strat column? So maybe show us an example and talk about kind of what's in the strat column and possibly correlations. If I know you had mentioned it during your talk about the correlating of strat columns that contain certain rock layers. So can you show us an example and kind of talk more about how it's done?
Yeah, so I think I mentioned this in my presentation, but a strat column depicts the rocks. So the oldest rocks are at the bottom, the youngest rocks are at the top, and basically it's showing all of the rocks that are exposed in the area that I'm mapping. We can create strat columns for different parts of the map area because we're working with sedimentary rocks. With distance, some of these rocks can vary, so like the grain size might change, or even certain rocks might not exist if they're localized in a certain area. The example I have here is of two strat columns that were taken within 2 miles of each other on the same map area. What these strat columns really illustrate is the variation in the units. So it can be difficult to correlate. So if you look at the two strat columns that I have here, there's a lot of variation going on. However, there's consistency within a few units here, which just happen to be the limestone. So if you look at the Avis limestone at the top of either of these strat columns, that's one way that we can correlate these strat columns, because even though they're in different areas, we observe the same map unit, we observe the same limestone in these two areas, so we can say, oh, we can basically connect the lines there. Also at the bottom, we have the Reynolds limestone, so that can be correlated across the distances of these two strat columns. And yeah, again, I just want to point out these are the only two consistent units that we have between these two strat columns. Other than that, it's just a bunch of red shale, some minor sandstones pinching in and out. So it's really the limestones are what are giving us the correlations here.
And I know you're focusing on the bedrock and mapping those units. However, in your talk, you did talk a little bit about fossils. And I mean, that's what I always want to talk about. So, can you share a little bit more about your favorite fossil and like why it's your favorite, and if it's one that you come across in your work?
Yeah, so I do have a soft spot for fossils. During my master's degree, I actually worked a lot with paleontology. My favorite fossil group would have to be cephalopods, so specifically the nautiloids. I Sadly they are not as common. It's not the most common fossil that I find, but I do find it enough. I don't know if I should mention this, but we did find it a few days ago. My last trip out in the field, we pulled out. It was 11 centimeters long. It was quite it was quite exceptional to find something like that. It it was more of a like the straight shell cone shaped nautiloids. There's different shell morphologies you can find. You might be familiar with the living nautilus, which has a planispiral shell, which you can also find that. But in the Mississippian aged rock that we found this fossil from, um, this nautiloid just happened to have a straight shell.
That's awesome. And so we just have about one more minute left for this interview. And I was wondering, thinking about, you've been with the West Virginia Geological Survey for about 3 years now. What do you think comes next for you? So you've been there. Do you have any professional goals that you want to accomplish, or where do you see your career going from here?
Oh, geez, that's a great question. So really enjoy my job at the survey. I think for the next couple years, I do want to help finish out some of our major mapping goals. I've been, like, as I mentioned, mapping in southern West Virginia, the southern part of the state, where we're really we've made a lot of progress in more recent years, mapping at the highest resolution that we have. That's 24K, and so I have really enjoyed being a part of that process. In terms of moving on, for future careers, I mean, I am interested in working for the state government. I think I really enjoy my job right now because of how well-rounded it is. Not only am I involved with bedrock mapping, which that's my primary position here, but I also get to help with our on-site museum, which is a lot of fun. So I get to do a lot of research and identification of different donations we might get, fossil donations from different donors. But moving forward, I think that I definitely like research-based work. That's one of the things I love most about my job now. I do love the field work component. It's not written off for me that getting a PhD is not written off completely for me. There still might be that potential one day. But yes, as far as I'm concerned right now, I'm pretty content at where I am. I'm not saying I'm going to live here, or I'm not saying I'm going to be working here forever, but I think it's a good place to get your foot in the door. This is my first real geology career, and I've had a lot of support through this job and just through my bosses, and I feel like I would have the support to move on to any other position that I would like to have, whether it's in this survey or a different survey, or even just any other type of sedimentary geologist position out there.
That's awesome. I think that speaks to a lot of people that are in that early career stage where having the experience, especially with first job with geoscience, getting the field experience, having the lab experience, dealing with rocks and fossils. It sounds like you have a very well-rounded experience that you can then go from and kind of pick and choose which roads you want to follow down. So it sounds excellent. And Shadya, thank you so much. We are out of time right now. Thanks for the presentation and interview. And we are going to now take some time to ask or answer questions from the audience. So thanks so much again for today.
Yeah, thank you.
So thanks for joining us, and feel free to keep putting questions into the chat. Shadya can address those as we go through the next 10 minutes or so. So to get things started, though, can you tell us a little bit more about the West Virginia survey and what you all have to offer?
Yeah, so we're we're a state agency, and so we offer data for the public, which has specifically, I can speak about the Bedrock mapping data that we've been able to offer for free to the public through our website. So we have a number of different resources, such as our Bedrock map, our interactive geologic map, which is on our website, which I can send a link in the chat if anyone is interested. But basically that shows our mapping at its 1 to 250K scale, which is the original Bedrock map that was made in 1968, but we have a simplified geologic map, and then we have a GEMS conversion of that same scale. And then we have more recent mapping, which has been done at 1 to 24K scale, which that's the type of mapping that I've been doing. So we don't have that for a full state coverage yet, but we're working on it. And so we also have digital files available for download and for free, which that's actually the most important link that I could give you. So all you have to do is go to our website, and you can request any area of West Virginia. And if you're looking for a certain quadrangle or a certain area, you just fill out this form, and then we get back to you pretty quickly, I want to say. I'm not sure what the turnaround time is, but yeah, this has been something we've been very proud to just share with the public, because you know, we've put a lot of work into our maps and our data.
Awesome. Thanks, Shadya. And I didn't know if you noticed, but we had a lot of people liking the fossil part of your talk, which is exciting. And our first question, actually, from the audience is about that. Someone has collected similar looking fossils in the locality Burns, posted near Uniontown, Pennsylvania. Have you all tried cooking these limestones for microvertebrates, or do you know if anyone at the West Virginia Geological Survey is doing similar work to this?
Okay, so short answer, I'll try to keep it short. No, we don't do micropaleontology analysis yet. We have kind of talked about it. We do have a paleontologist here on staff. However, like, the survey hasn't done, at least to my knowledge, done much in the micropaleontology realm. That is something interesting, but we also have a lot of other priorities that we've been focusing on, but I can see how that would be helpful, specifically, like, I don't know about vertebrates, but like some of the invertebrates, like just looking at that from like a biostratigraphic standpoint, that could be very helpful. But we would probably have to send out samples to a lab or to somebody that specializes in that.
And another quick follow-up question for the fossils. Someone asked if you are based in Montchâteau, and if the fossils that you find in the field, such as the one that you talked about today, get added to the collection there.
Okay, so that's a great question. So they get added to my collection. I mean, honestly, usually if I find something really exceptional or something that I think belongs in the museum, I'll donate it. We have a lot of stuff. We have, as I mentioned, there's a museum on site which is free, which you should come visit. But we also have an entire building that is just partially reserved for collections. So, like, we have a lot of fossil collections and different rocks, different artifacts and stuff like that. So I feel like I'm totally straying from what the question was asking, but they do, yeah, we do keep that stuff. And a lot of times when I collect stuff in the field, it's just for my own reference. so I don't have to go back somewhere, or if it's something, different or something important, then it's nice to keep that.
Great, thanks, Shadya. And there are two questions related to technology in the field, so I'll ask them kind of back to back. The first question first popped up in the Q&A section, asking if you'd ever had used a digital brunt compass program like Field Move Clino, possibly.
Okay, yeah, so I personally have not used that, but one of the instructors I went out to field camp with, he was a big advocate of using that, and I watched him use it, and it seemed pretty accurate. I personally haven't explored into that.
Oh,
your mic cut
Lindsay.
out a little bit there.
Sorry, do you want to try muting and unmuting yourself, Shadya? No, we can't. All right, well, due to these technical difficulties, Shadya, if we might kick it to our post-production slides, and if you can possibly follow up with all these questions. We have a list of going, we have about 5 more questions we were hoping to ask you, but if you can answer these questions, and we'll send them out to the people as along with the recording.
And if there's any questions that you didn't get to submit today, I just put our email in the chat, and you can send us additional questions for Shadya to address.
Awesome. So thank you again, Shadya, for sharing your time, expertise, and insight with us today. And next up in our early career professionals and mapping webinar series is Madeline Kelly, a geographer and geomorphologist at the University of New Orleans. She'll discuss using, making, and sharing maps on February 8th. View more details about the talk and register using the link in the chat. And if you are an early career professional in mapping or know someone who is, please encourage them to apply to be a speaker in this ongoing series. Applications are now open for the fall 2024 speakers. Visit, again, the link in the chat for more information, and please pass the link along to any early career professionals who might be interested. And lastly, have natural disasters influenced your academic or career path? Do you have thoughts on how well society is prepared for the impacts of climate change? If so, AGI is inviting students, postdocs, educators, and geoscientists from across the United States to provide feedback related to the impacts of climate change. For more information about this NSF-funded project and to participate in the project, visit, again, the link in the chat. Thank you, everyone, for joining us today, and we look forward to seeing you next time in February.
Thank you.